For thousands of years, humanity has measured time the same way, by counting intervals between 2 points. From ancient sundials tracking shadows to modern atomic clocks counting electron vibrations, every method has required a starting point, a time zero. But what happens when you need to measure events at the quantum scale, where then and now blur into a fuzzy reality? Where starting points are impossible to define. Today, we're exploring a revolutionary breakthrough from researchers at Uppsala University in Sweden. A quantum watch that reads time without ever needing to start counting. As lead researcher Marta Berholtz explained, the benefit is simple yet profound. You don't have to start the clock, you just look at the interference structure and say, okay, it's been 4 nanoseconds. To understand this quantum watch, we first need to meet the superheroes of our story, Rydberg atoms. These are the overinflated balloons of the quantum world. Using lasers, scientists can push an atom's electrons into extremely high-energy states, sending them orbiting far from the nucleus. When electrons enter these Rydberg states, their behavior is described by what physicists call wave packets. Think of them as the unique quantum signature of how these excited electrons move and behave. Like dropping multiple stones in a pond, when these Rydberg wave packets interact, they create complex interference patterns. And these patterns hold the key to our new way of telling time. Here's the brilliant insight. Each unique interference pattern created by interacting Rydberg wave packets corresponds to a specific point in time. The researchers discovered they could create what they call quasi-unique beat signatures, or QUBS, essentially time fingerprints that are so distinct, each one marks a unique moment in the evolution of the wave packets. Think of it like this. Instead of timing a sprinter from start to finish, you'd have various runners moving at set speeds around them. By observing the patterns they create relative to each other, you can determine exactly how much time has passed. No starting pistol needed. The team brought this concept to life by exciting helium atoms with laser pulses and ultraviolet light. They found their quantum watch could measure events as brief as 1.7 trillionths of a second with astonishing precision. Errors no larger than 8 femtoseconds. To put that in perspective, 1 femtosecond is to a second what 1 second is to about 32 million years. As Marta Berholtz noted, this isn't just a laboratory curiosity, it solves real problems in quantum research. Keeping accurate track of time at such timescales becomes complicated. A quantum watch is a tool that has to be used whenever a pump probe experiment is running on a femtosecond timescale to make sure that the time is accurate. This technology is particularly valuable for pump probe spectroscopy, which studies ultrafast processes like electron movements in chemical reactions. The quantum watch provides these experiments with incredibly precise timing without the usual complications of establishing starting points. The future possibilities are extensive. Researchers suggest using different atoms or varying laser energies could create entire guidebooks of quantum timestamps tailored for different experimental conditions. The team is already investigating how far electrons can travel from atomic cores and how we might control their journeys. The quantum watch represents more than just a new timekeeping method. It shows us that sometimes solving deep scientific problems requires completely reimagining fundamental concepts. Even how we measure time itself can be transformed when we view it through the lens of quantum mechanics. In the words of the researchers, this is a fully quantum mechanical watch that doesn't utilize a counter at all. It's a tool born from quantum weirdness that might ultimately help us unravel more of the quantum world's deepest mysteries. For deeper details, you can read the full study Quantum Watch and its intrinsic proof of accuracy in Physical Review Research. Thank you for watching.